Hey, hello everyone and greetings. Welcome to the 46th session of the online Optom learning series. I think good evening, good afternoon to people, and a very late good evening to our speaker for today, Dr. Vinod. He is in Australia, and I guess it's about 11 p.m. there. Let me just introduce to you our speaker for today. So today we have Dr. Vinod. He is a lecturer at the School of Optometry and Vision Science at the University of New South Wales, Sydney, Australia. He is also the course controller for the contact lens course at the university. He obtained his basic optometric qualifications from the Bosch and Lomb School of Optometry, associated with the LV Prasad Eye Institute in India, and later he completed his PhD from the UNSW, Sydney. His main area of research is in orthokeratology and lens decentration. He has numerous publications in contact lenses as well as other optometry related topics and have presented papers in national and international conferences as well. He has also served as a reviewer for the international journals including Optometry and Vision Science, Clinical and Experimental Optometry, to name a few. And today he is with us and he is going to talk to us about the novel contact lens surfaces which helps to enhance comfort. So welcome, Dr. Vinod, and I'll leave the screen time to you now.
Firstly, thank you, Fakhruddin, for inviting me to give this presentation. And a warm welcome to everybody who just joined this evening. For me, it's evening, so I'm saying evening. So this evening for this particular talk. My name is Vinod, as Fakhruddin mentioned. And right now I'm sitting in my office presenting this talk for you guys. You might be surprising why I'm presenting a contact lens surfaces when my core research area was orthokeratology. It's because recently I had to be a part of the manuscript where we reviewed contact lens surfaces in terms of comfort. We were particularly looking at the wettability part of it. So as a part of that exercise, we had to review a lot of journals, and then I gathered a bit of knowledge in this area, even though I'm not researched particularly in this area. So I thought I should just share this knowledge with everybody. So I'm not the leader in the topic, but at least I've gone through the literature related to this one. That's why I'm sharing this knowledge with you guys. So the topic that I'll be presenting here is novel contact lens surfaces to enhance comfort. So to begin with, the learning objectives for this particular talk is that we'll learn about the definition of contact lens discomfort. We will be learning about lens surface properties and characteristics governing contact lens discomfort. Particularly, we'll be looking at three different properties or characteristics. Then we will be looking at discussing about current silicone hydrogel lenses and their surface properties. Again, comparing looking at how these lenses perform against these different properties. And finally, we'll also talk about the new contact lens surfaces. So contact lens discomfort is a really big word in the field of contact lenses currently, because the prevalence of contact lens discomfort is huge. So of course, different studies give different numbers. But what, in a nutshell, if I were to put this one, is that about 50% of our contact lens wearers are likely experience contact lens discomfort. This is important because if you look at the top reasons, the leading cause for contact lens dropout, that means discontinuation of contact lens, is comfort. So given this background, there's a great emphasis given for contact lens discomfort. In 2013, there is a TFOS international workshop where particularly contact lens discomfort was discussed. And the researchers in the field have come to a conclusion and define what contact lens discomfort is. So contact lens discomfort is defined as per the a TFOS International Workshop is a condition characterized by episodic or persistent adverse ocular sensations. So the things that you need to take here is it is episodic or it could be persistent as well. And it is related to contact lens, where obviously we are dealing with contact lens discomfort. It may be either with or without visual disturbance. So vision is not a hardcore criteria, but people may have vision related issues or may not have vision related issues. Okay, so and why this is happening is because of there's a reduced compatibility between the contact lens, the lens that we are wearing, and ocular environment. So ocular environment is ocular tissues or conjunctiva or cornea, various other things. This can lead to decreased wearing time, and often most of our patients do complain that they are unable to wear for longer durations of time contact lenses. So, and also some people actually discontinue contact lens wear. Often patients do have contact lens discomfort, and when they have this one, what they do is that's how contact lenses have to feel, and then 50% of them just stop wearing contact lenses. They might go for glasses, or even they might actually just go to another practice to get another type of contact lenses. So the problem is not solved yet. So that's the reason there is a big emphasis given on contact lens discomfort. So again, in the same publications, there is a classification of contact lens discomfort. As you might see, it can be contact lens related, or it could be environment related as well. So I'll keep this environmental thing aside, and I'll come to the contact lens side just for this presentation. And in particular, I'm not looking at the design fit and wear and lens care. So there are other reasons why there is a contact lens discomfort, and not necessarily what I'm going to talk, which is materials. So in this talk, I'm particularly focusing on material. So you have to particularly keep attention to other reasons for discomfort also when you're making decisions in clinic. So not necessarily what I am talking. Okay, so we know soft contact lenses. Again, in this particular talk, I'm focusing only on soft contact lens materials because that's what 98% of the times practitioners tend to prescribe. Contact lens materials are broadly, classified into two categories. One is the hydrogel lenses, which were very popular. Even now, they are popular, introduced in 80s and 90s. One of the major disadvantages with these, even though they were comfortable, was hypoxia. Hypoxia is the main reason because the decay by T, or the oxygen that is reaching corneal surface through the contact lens material, it was relatively poor. One way to increase oxygen permeability to the material was to increase water content. But there was an issue. As you increase the water content, there are other issues such as lens deposition. And one way this deposition problem was solved was by introducing disposable contact lenses. But later, there was a big breakthrough, and then silicone hydrogel lenses were introduced in the late 90s. And this was a major step in the field of contact lenses, because it eliminated, it was thought because hypoxia could eliminate not just hypoxia, but also any contact lens related infection. But unfortunately, it was a big disappointment that it didn't deal with complications related to contact lenses, but definitely it has eliminated problems related to hypoxia. One major problem with silicone hydrogel lenses was that the material consists of siloxane components. PDMS is a polydimethyl siloxane, and tris monomer generally are the core component of silicone hydrogel lenses. And these siloxane components make the lens surface hydrophobic. Hydrophobic means, it's not water loving, it's water hating surface. We want lenses which are water loving, because when you place it on the eye surface, we have TS on the eye, and then we want the TS to easily spread on the eye contact lens surface. So but unfortunately, these materials are hydrophobic and therefore it tends to attract deposition. Of course, there was deposition with hydrogel lenses also, but silicone hydrogel lenses particularly are lipid kind of deposition, and also there was denatured protein deposition. So the question comes obviously is because now we have silicone hydrogel lenses, it is increasing the oxygen permeability, but are they more comfortable than hydrogel lenses? If you look at the literature says that initial publication reported that silicone hydrogel lenses are way better than hydrogels in terms of comfort. But later on, same authors who reported that they were comfortable also reported that actually the comfort is similar between silicone hydrogel lenses and hydrogel lenses. And there are many reasons given out why they were similar, because one of the reasons why initially the silicone hydrogel lenses were thought was better because those studies generally compared wearers' comfort with their habitual lenses. So what they were previously wearing, they compared with that. And so usually whenever you move as somebody from one type of contact lens or one type of modality to another type of contact lens, which is a new one, obviously there's some kind of placebo effect in that, and usually newer thing tends to be better, so people generally think that it is a comfortable one. So obviously it will affect the rating subject to comfort ratings, and then they eventually said that they were better. But over time, more and more studies have shown that the comfort was similar in both silicone hydrogel lenses and hydrogel lenses. But having said that, it is not the other way around is true too. Like, you cannot say hydrogel lenses are more better than silicone hydrogel lenses either, because it's not just the material, but it is the much more complex area. It's beyond just the material. But again, as I say, I'm only dealing with the material here, so I'll be concentrating only on the material. Now, what affects the surface properties, and how this will relate to comfort? The things that when we look at contact lens surface properties affecting the comfort are the friction, wettability. Wettability can also be either in vitro or in vivo. I'll come back what in vitro and in vivo is. And then the surface deposition. So let's look at the friction on lubricity first. So when we talk about friction, the easiest way to explain friction is by taking the example of Michael Jackson, because Michael Jackson not only defies gravity but also defies friction by his famous moonwalk. Friction is a resistance to the movement on the surfaces, and obviously, as you can see in the moonwalk, Michael Jackson does very effortlessly. This is because not only that Michael Jackson does this very easily, and it has got his own charm in it, there's a lot more prior preparation in it. He reduces the friction on the surface, and in this case, the surfaces are the floor there and also his shoe. So he ensures that there's a reduced friction there. And of course, as you can see, he does it so effortlessly, and I always admire his act of moonwalking. So now coming back to the physics of it, what friction is? The friction is the force resisting the relative motion of surfaces, right? So we have particularly when it comes to contact lenses, we have ocular surface, you've got contact lens surface, you've got eyelid surface, and the palpebral conjunctiva. So we have different surfaces, and then somehow there is some resistance occurring, and then this will affect patients or wearers' comfort. And friction is also an indicator of lubricity in the eye, or even it could be if it is outside the eye, it could be, we are talking about the lubricity between among various mechanical tools also. For example, some car parts or machine parts. We also talk about lubrication and friction there as well. But here we talk in terms of eyes lubrication and also friction. So What friction and how friction is measured? Once a friction is measured, it is denoted by a something called coefficient of friction. And this coefficient of friction for a normal cornea, healthy cornea, it is reported to be about 0.01. That means if somebody gives us that kind of number around 0.01, that means it is supposed to be comfortable. So greater the coefficient of friction, poorer is the comfort. So we want it to be closer to 0 basically. So anything closer to 1, it is not so comfortable. And this particular coefficient of friction is easily influenced by various ambient situations. It could be temperature, pressure, velocity. So whenever you're reading literature or related to friction, you got to be careful and how the numbers are generated. And I know that when I visited India recently, and also around the world, there's greater research happening in relation to friction in contact lenses, and this is an emerging field of research in contact lenses, and this is called tribology. So if anybody is particularly interested in getting more research work done, maybe this is an area to pursue. Now, we talked about friction and lubricity. The next thing that I will be talking about is the wettability. We all learned that about wettability to some extent in our optometry lectures. So wettability is the ability of the tear film to spread on a contact lens surface. So if I put it very simply that way, okay. So it has its influence both in lubricity and also in friction. So wettability can be it is dependent on type of lens. It could be whether we are dealing with the hydrogel type of lenses or silicone hydrogel lens types as well. In hydrogel lenses, we know that there are hydrophilic and hydrophobic moieties within the bulk of the lens matrix. So if a lens, when somebody puts the lens on and lens surface dries, what generally happens is, because there is a hydrophilic, which is water-loving side, and which is hydrophobic, which is a water-hating side. So hydrophilic ends, the moment the lens dries, the hydrophilic ends tends to move inward towards the matrix, and hydrophobic part, it comes outside, and then it faces to the surface or to the air. So because of this reason, the surface becomes always dry, and of course, this wettability has a problem. Poor wettability has a problem in relation to deposition, or it could be because of the comfort as well. In silicone hydrogel lenses, the phenomenon is a little bit different. In silicone hydrogel lenses, lens dries because, not because of the hydrophilic and hydrophobic moieties, but because the material nature. We discussed that the siloxane components in the lens material are inherently hydrophobic, and that's why lens is hydrophobic. And hydrophobic surfaces attracts deposits, and these are particularly lipid types of deposits. Deposits also occurred in hydrogel lenses. There were more protein and also lipid and also other types of deposition. But in case of silicone hydrogel lenses, very focused deposition was on lipids. So how do we measure wettability? So as I said, there has been in vitro wettability and in vivo wettability. In vitro means anything that we measure in the laboratory. So in laboratories, we have contact lenses. You can have contact lenses and then look at the wettability on the contact lens surfaces. So the way we do is, I'll explain that in the next slide, but we're simply measuring the angle formed by the drop placed on the contact lens surface. So the angle is measured using goniometer, and if the angle is less than, if the angle is less than 90 degrees, we call it as hydrophilic, which is actually, in fact, it's better. And if the angle is more than 90 degrees, it's hydrophobic, which is not what we want. And in vivo side, that means what we measure on the eye, we cannot directly measure contact angle, but in actual fact, we will be able to measure the non-invasive tear breakup time. And there are several ways of measuring non-invasive tear breakup time. One that could be using a TS scope. People these days also use a topographer, Placido disc type topographer, where you place reflections on the eye surface and look for any breakage in the contour of the rings that are projected onto the eye surface. So again, in laboratory, we measure contact angle. In clinical measurements, we look for tear breakup time. And even though I said less than 90 degrees is hydrophilic, but what we want is very small angle. I'll explain that further in the next slide. So how wettability is measured? There are different types of different ways of measuring wettability. We have Sessile drop technique, captive bubble technique, Wilhelmy technique. In Sessile drop technique, as I mentioned in the previous slide, we just place a drop on the lens surface and then measure your angle. And the type of angle that is measured is called advancing angle. I'll come back to what is advancing and receding angles in a moment. In captive bubble technique, rather than we place a droplet of fluid, we actually use lens which is immersed into a liquid, often which is a water. And in this, we measure both advancing and also receding angles. An advancing angle is when I put the notes here. An advancing angle is when the liquid is spread over the surface. It's as if that the tears are spreading over the surface. We want to be able to measure the angle as the tears are spreading and also as the tears are withdrawing. Similarly, that if you mimic in a laboratory setups, in this case, if the bubble is shrinking, in that time the tears or the fluid in wherever the lens is immersed is actually getting onto the lens surface. So therefore, what we're measuring is advancing angle. And if the bubble enlarges, if the bubble shrinks, we measure advancing angle. And if the bubble enlarges, then we are measuring the receding angle because the spread of the water is going away from the surface. And similar thing is also measured using a Wilhelmy technique. So you dip the lens into the fluid and also take it out. As you dip, what we measure is advancing angle, and as you take it out, you measure a receding angle. And this will obviously happen at the site of where the substrate or the surface is touching the fluid, and you'll have to look at that particular site using a goniometer to be able to measure the angle. And why we are discussing about these angles, even though this was discussed in our basics during our optometry, is because when I'm quoting how different lenses perform, I'll be using both advancing angle, receding angle, and also what is called as contact angle hysteresis. Contact angle hysteresis is calculated as a difference between both advanced angle and receding angle. Now the question comes is, what are we looking at basically? So we have different angles, so which one more are we looking at? When we are looking at contact angles, we want advancing angle to be low, we want the receding angle to be low, and also we want the contact angle hysteresis also to be low to be able to say that a contact lens surface is perfectly wettable. So that's about in vitro wettability, and now let's talk about the in vivo wettability, that what happens, what we see on the eye in a clinical setup. We know that contact lens is a foreign body, and the moment you place it on the eye, it disturbs normal architecture of the tears. So we have normal precorneal tear film thickness, which is about 7 to 10 microns. So that's about 7 to 10 microns. The moment you place a contact lens, it actually reduces the thickness by about half. So the pre-lens tear thickness is measured to be around 2.31 to 6.4 micrometers. And Obviously, now given that the pre-lens tear film is so thin, there is a greater evaporation and on the surface of the contact even within 1 hour. So the pre-lens tear film stability is measured to be 6.1. When if there is no lens, the tear film stability is about 33 seconds, which is quite long. So that means by putting a lens, we are basically giving faster breakup time over the contact lens. Now, what this means is there is not sufficient tears, lens is drying up, and this will attract deposition. So there is surface deposition. And what we know in terms of surface deposition? Surface deposition depends on what kind of lenses we are dealing with, whether it is hydrogel lens or silicone hydrogel lens. Hydrogel lenses, as we all know, that it is classified according to FDA into 4 groups. So we have FDA group 4 and group 2, which are high water content contact lenses. Either it is ionic or non-ionic, both are prone to deposition. FDA group 4 is more prone for lipid deposition, whereas FDA group 2 is more prone for lipid deposition. Silicone hydrogel lenses, on the other hand, reported to have lower amounts of protein deposition than hydrogel lenses, and this is partly because of the material nature. And also we discussed that hydrophobic surfaces on silicone material generally attracts more of lipid deposition. One of the lipids which is famously seen in relation to silicone hydrogel lens is called lysozyme. And this denatures and then builds up on the lens surface. This is an important deposition because when it happens on the lens surface, it actually triggers one immunological response on the eye, and it can eventually lead to papillary conjunctivitis also. Lipids from meibomian glands are also likely to lead in the poor surface wetting as well. So it's not just the lysozyme from the tears, but also lipids coming from meibomian glands also has been shown to deposit on the lens surface. So again, we have hydrogel lenses and silicone hydrogel lenses both deposit. And why we are discussing about a deposition in relation to comfort is because there are strong correlations found between subjective comfort and active deposition of lysozyme. And of course, now again I mentioned that in the rest of the talk I'll be more focusing on silicone hydrogel lenses than hydrogel lenses. So that's why I'll be talking more about lysozyme than normal protein deposition that can occur in other types of contact lenses. Okay, so what's the hunt for? So why are we discussing so many things? Is because lens surfaces with low friction coefficient is what is required, and we want a more wettable lens surfaces, and also we want surfaces that actually discourage deposition. So if we are able to tick all these boxes, obviously we are going to have a better lens surface and therefore a comfortable lens wear. Now, how do we achieve this? How can we achieve this? Is we can modify lens surfaces. You might have heard of several other types of materials where the hunt is more for hydrophobic rather than hydrophilic types of surfaces. For example, the car example that I'm showing here. So, but whereas in contact lens industry or contact lens area, we are more looking for hydrophilic surface. So it is slightly different to what we see in the other surfaces in the material industry. So in contact lenses, how do we modify lens surfaces so that the contact lenses are more wettable and become more comfortable? How we do it is, when it comes to lens, we can apply lens coatings. We can make modification to the lens surfaces. We can also actually inject or incorporate internal wetting agents. I'll come to that sooner in the next few slides. Then we have blister pack solution. The package that we have it's not just saline that is sitting here. Initially, it used to be just normal saline, but over time, people have understood that the material that comes in the blister pack is not just the normal saline, but it also has surfactant agents. So because surfactant agents influences the surface tension and also interfacial tension, the lens will become more wettable while it is being soaked in the blister pack, and the moment you place it on the eye surface, it's supposed to be comfortable. And finally, once the lens is on the eye surface, people tend to use lubricants, and therefore thereby they reduce friction and then promote comfort during lens wear. So there are different ways to promote comfort. But what is more I'm going to focus on is the lens coatings and modifications. Okay, so the first question to be asked is, do lenses need surface coatings or surface modifications? Hydrogel lenses generally do not need surface modifications or surface coatings, because if there are any non-wetting problems associated with hydrogel lens, we generally incorporate more wetting agents. So when I say wetting agents, you have a bulk polymer, and then we tend to add extra copolymers or monomers into the matrix so that we make the lens more comfortable. So a few examples of wetting agents, polyvinyl alcohol or polyvinyl pyrrolidone are some of the examples where we can use to enhance wetting properties of the hydrogel lenses. But silicone hydrogel lenses are different. Silicone hydrogel lenses predominantly have silicone as a component, inherently hydrophobic, and therefore usually we need coatings there. Okay, so now I take this table here. I particularly chose a few lenses, not all the lenses in all generations. If you split contact lenses or silicone hydrogel lenses into different generations, we have, I'm quoting here 3 different types of lenses in generation 1, and in generation 2, 2 lenses, in generation 3, I have 1 lens. The reason I've chosen these particular lens types in these 10 generations is because I have the data for friction or wettability or deposition, so I've chosen this one. So there's no particular reason why I've eliminated others. I've already given you the reason. So now coming to the first generation contact lenses, Lotrofilcon A is the material, focus night and day, which is the first silicone Filcon A at the same time but they were launched. I was fortunate enough to work with these early lenses in my research as well. So Lotrofilcon A and Filcon A both are silicon-rich materials, are inherently hydrophobic, and therefore these lenses required a special coating. Lotrofilcon A uses what is called as a plasma coating, and which is applied in a plasma reactive chamber, and this leads to continuous coating which is of 25 nanometers thick. On the other hand, we have Filcon A, which is where we also apply coating there as well, but this is not actually a coating per se, but it is a kind of application of different glassy islands which renders hydrophilicity on the lens surface. So these are islands, so that's not continuous. So whether the plasma coating does better or the islands do better, we will see in the next few slides. Okay, so then there's a second generation silicone hydrogel lenses. The example that I am taking in my talk is Lotrofilcon B. The important modification between Lotrofilcon A and Lotrofilcon B here is that the injection of hydroglide, a moisture matrix, which actually incorporated within the lens matrix, which actually, sorry, not matrix, but on the surface. Apart from the lens coating, what we also have is a hydroglide moisture matrix. So this will render comfort by 2 reasons. One is the coating, and also we have moisture incorporated within the lens material. So let's look at how these different lenses will perform in terms of friction and lubricity. So And this particular chart here is coming from from one of the J&J's notes. And actually, they have given only numbers, but I have put that into a graph format so it'll be easy for us to understand. So friction coefficient, remember anything closer to 0 is good and anything closer to 1 is not so good. So look at the first generation contact lenses. They have friction coefficient on much closer to 1. Although air optics is slightly exceptional, you see that the generation 1 actually not so good. And while we need a lens which is about 0.01, these lenses have a friction coefficient which is slightly higher. And you might notice that generation 2 and generation 3 lenses are relatively better in terms of friction coefficient. And studies that looked at the relationship between the lens coefficient and a coefficient of friction and subject to lens comfort did say that there's a strong relationship between a coefficient of friction and subject to comfort. So this is something more and more people are looking into, not just by looking at certain types of lenses, but looking into to different types of, including frequent replacement or daily disposable and many other types of contact lenses. Now looking at the in vitro wettability, so in terms of contact angle, how this will perform. Remember we were discussing about advancing and receding and hysteresis angles before. So if I put that information here using these materials that I have discussed earlier, you have, as you can see, among the first generations, a pure vision is having contact angles really high, especially the advancing angle is pretty high, and we have receding angle here, and the difference is here. So we did say that in order to say a particular contact lens is relatively better, we want these to be lower, and also contact hysteresis angle should also be lower. So in that case, you might say that the focus night and day lens, which is the first generation contact lens, is doing relatively better with its peers. And later generation contact lenses are more or less the same. I'm not quoting any statistical number here, but looking at the graphs, the performance seems to be more or less the same. But yeah, in terms of receding angles, you see that the later generations are doing, sorry, not receding, the contact lens hysteresis, the later generations are doing better, with exception to focus night and day. Okay, so then comes to in vivo wettability. So that means how now these contact lenses are actually doing better on eye surface. Unfortunately, not much research has actually looked into this particular thing, that how these lenses, when placed on the eye surfaces, will actually perform, except for one. That one particular study actually concluded that that no matter what the surface properties are, the T-film spread or stability is more or less the same between all other lenses. So what the study concluded is that the TFM stability remains dependent on pre-lens TFM thickness, composition, quality of the TFM, and many other external factors, not necessarily the surface properties. You have to keep in mind one thing, obviously, because you have to see more and more studies in order to take informed decisions on to say whether a particular type of lens is doing well or not. So more research is required in this area to be able to say that a particular lens is better, or should we only depend on the environmental factors. Now, surface deposition. Remember, I was talking about the lysozyme deposition. So I'll be taking the example of lysozyme deposition in these lenses. As you can see, the amount of lysozyme deposited on contact lenses is different. And of course, I do not have numbers for generation 3 contact lens. So I have generation 1 and generation 2 here. And as you might notice that the pure vision has highest deposition, and for other lenses are relatively low lysozyme deposition. And again, I say why we are discussing about deposition, because if you have lens that is deposited, eventually lead to not only discomfort but also papillary conjunctivitis sort of problems. So when it comes to one particular study, actually looked into what actually makes the lens to attract more lipid deposition. One particular study looked into generation 1 and generation 2 contact lens. Generation 1 with lens coating, generation 2 not with lens coating but with internal wetting agent. So Lotrafilcon B, which is generation 1, has actually shown greater affinity to lysosome deposition only when you have a particular protein that is present in the eye, which is called lactoferrin. So if you have lactoferrin and lysozyme, the lysozyme deposition was more. Okay, so but in another type of contact lens, which is if you see Sessile should have been aqueous, no lysozyme uptake it was there, and without the presence of without the presence of lactoferrin. So that means it's not just the lysozyme just going and sitting because it wished to do that, because it is a much more chemically directed deposition, and these are obviously studies which are looking into laboratory work, but not necessarily work that is done on real human eyes. So the take-home message from that study was that lens deposition is a response to the overall material composition rather than just whether it is coated or not coated. Now there are tear film stability studies, particularly looking into whether there are deposition present or not present. So we were discussing about many other things, but we have not looked into whether there is a deposition present, and there is how it is performing clinically in terms of breakup time or not. So one study was done particularly looking into it, and in this study they have categorized up people into deposit prone and not deposit prone. So all the deposit prone individuals were put on two different types of contact lenses. Here we have Lotrafilcon B, which is generation 1 silicone hydrogel lens, and then we have generation 2 silicone hydrogel lens, which is supposedly bi-weekly. So and we had participants participating in both these types of contact lenses, and lenses were worn for about the duration of 2 months. And what they looked into is the tear breakup time. So they looked for the tear breakup time and also minimum protected area. So if the minimum protected area, that means it's wettable, is greater, that means that the surface is doing better. So as you can see, the breakup time, in terms of breakup time, there was not a big difference between Lotrafilcon B and Sessile A lenses. However, when it comes to the protected area, it said that Lotrafilcon B outperformed Sessile A. So again, in this case, we have coating here, but we don't have coating here. There are other types of lenses. I'm sure that you guys are more familiar with these lenses, which are total dailies one. And this is a daily disposable type of contact lens, which has got two types of material. One is silicone on the central core part, and we have hydrophilic on the gel on the outer surface, which is about 6 microns in its thickness. And the outer surface has greater amount of water content than the core component, which is only 33%. So the purpose here is it retains the values or the benefits of silicone, while also have the benefits of hydrophilic surface gel, which promotes comfort. So if I add this into this and looking at the coefficient of friction is pretty low. And as you can see, as we have already discussed, that if the coefficient of friction is lower, and this should lead to a more comfortable wearing contact lenses. I'm not sure from a practice point of view how you see total dailies lenses in terms of wearer's comfort. And if there are other studies done and looking at the contact angle hysteresis, which is less than 10 degrees, to my understanding, there's no lens at this stage which actually beats the contact angle hysteresis, which is so low. And when compared to other generation, of course, this is A is generation 3 lenses, and when it compared to other generation 3 types of contact lenses, this particular lens outperformed in terms of wettability and also breakup time. So what we understand from the current silicone hydrogel lenses, so we understand that the coatings are internal surfacing agents. So should we have coatings, or should we have actually promote internal surfacing agent? Because we have seen some mixed results from the studies that have been done. And one thing definitely comes up is the friction. Friction measurement is very important, and because this is strongly correlating with patients' or wearers' comfort. And there have been some inconsistent results, particularly with in vitro surface properties, whether they actually match the clinical observations in terms of breakup time and etc. So whether wetting angle or contact angle actually relates to clinical observations or not. And then we have also seen lens deposition is the response. This could be the response of overall material composition than just based on the surface coatings. And the fast deposition of lipids may be result in poor clinically wettable contact lenses. So this requires further investigation. And one of the reasons, one of the things that we may require is that we need a lens that are anti-biofouling surfaces. That means surfaces which discourage any kind of a deposition on the lens surface. So what we have on offer. So I'm going to, there are more and more materials are coming, but I'm taking examples of 4 different materials which are currently being investigated. And I would have to tell you guys that these are still on the experimental stages. So it may take time for it to actually commercialize. So the first of its kind is called the layer by layer assembly. A layer by layer assembly type of application onto the lens surface. So layer by layer application is not necessarily done in contact lens side, but it is actually done in many other material substrates, including contact lens. So this is one of the major discipline which is coming up in the field of nanotechnology. So what is happening here is in layer by layer assembly, you have a substrate. When I say substrate, in our contact lens terminology here is our normal contact lens. So you have a contact lens of a particular charge. You know that from our understanding of the FDA grouping, we know that there is a bit of charging that always comes on the lens surface. But this charge is one of the reasons why deposition happens. So what we want to generate a neutralized surface. So this particular substrate is dipped into a series of solutions of both polyions and polycations. So if you have a positive charged surface, you can dip that into an electrolyte which is having a polyanion, and therefore you have the surface now with cations and anions. And again, dip into a clear solution, and then you dip it back into a polycation, and you can clear that, and then you can repeat the cycles n number of times. So the number of times that, or number of cycles that you want to do, is depending on how many layers that you want to apply to the lens surface. Now the question obviously comes that we are saying layers, so what is it going to do? The advantage with this one is that it is a multi-layer structure, but within the controllable thickness, which is the greatest advantage of this technology. And even though, as from the sounds of it, you think that there is actually forming layers and layers, but in fact what is happening here is the ions are actually doing interpretation interpenetration. So that means actually they're clumped into both anions and cations after several applications of these layers. So that means the resultant is that it's going to be more kind of neutral surface, and that kind of surface is good because it will not attract deposition, because one of the reasons for deposition is it tends to attract oppositely charged tier elements or tear film elements or tear film chemicals, and that's how the deposition happening. But by making a lens more neutral, that kind of protein adsorption can be minimized, and at the same time we can also improve wettability of the lens surfaces. So that's the layer by layer technology. And this layer by layer assembly is actually applied for contact lens materials also, which is, for example, silicone hydrogel lens materials. So when it is applied onto silicone hydrogel lens materials, it is dipped into positively charged chitosan and negatively charged hyaluronic acid. And in an experiment conducted by these guys here, they have applied up to 5 layers, and with each layer of application, they have actually noted that the contact angle actually is becoming better and better. And also, again, these are laboratory studies. So the laboratory studies showed that there is reduction in the protein adsorption when they looked into human serum albumin and lysozyme. Now, another type of grafting, which is called as grafting HA or hyaluronic acid, by using a special technique called click chemistry. Click chemistry was introduced by Sharples, B. Sharples. He actually is a Nobel laureate who introduced this click chemistry. So click chemistry is a special chemical phenomena, so where one can isolate target specific molecules. So in our if I were to put this in our knowledge, or if to contact lens field here, we want certain molecules to behave or be in certain positions in our lens matrix. So hyaluronic acid is one particular material we want it to be available into the lens matrix. Okay. In general, what happens? Hyaluronic acid is even otherwise is used in contact lens materials. But the thing is, in order to get this into the lens matrix, you need to take several steps. But by using a click chemistry, what the material scientists have done is they were able to tether, or they were able to place these hyaluronic acid molecules at one particular area and then lock it there. So that is possible with click chemistry, and using that technology, the contact angle hysteresis has been reported to 12.8 degrees, which is fantastic. If the lens surfaces are treated using this click chemistry, the angles have gone tremendously down. Whereas when you're using untreated, if the lens surfaces are not treated by click chemistry, the angles were 55 degrees. And also, the studies have also reported that there was less protein and also lysozyme adsorption on the grafted materials. Of course, which is what we want. And we also have another type of grafting, which is now using a proteoglycan. So here the hyaluronic acid is a glycosaminoglycan derivative. So whereas here we have a proteoglycan here, which is a glycoprotein. And this is a mucinous glycoprotein, so it has lubricating properties, which is good for contact lens surfaces. So the PRG4 is actually derived from humans. Even it's otherwise is also present even in normal human eyes, but we want to get this onto the lens surface. So a recombinant human PRG4 is used. So recombinant technology is a technology where we take certain protein or any particular material, and then you genetically modify and then apply to wherever you want it to work. So in our case here, PRG4 is derived from human, and then that is applied onto the surface materials of contact lenses. So it is successfully grafted onto silicone hydrogel contact lenses in the laboratory. And the primary reason why this has been done is because it has got increased lubricating properties. These guys were particularly looking into the friction and contact angle, and the studies also have shown that there is a reduction in friction and also contact angle. Obviously, we have seen that if there is a reduction in friction and contact angle, there is a better comfort. And also, this study reported that there is a human serum albumin reduction and also reduction in adsorption of lysosome also. Now, I have another material, which is a polymerizing DMA. So DMA is dimethyl acrylamide, which is a kind of monomer that has swelling properties. So it actually swells at the moment you place it onto the knee. Hydro or water kind of material. So even otherwise, we have dimethyl acrylamide in contact lens materials, but this is usually injected or diffused into the material bulk. But what is more required? We wanted this particular DMA to stay on the lens surface. So we want it to be polymerized onto the lens surface, and this is done thermally to increase the lubricity of the lens. And again, this study also has shown there is a significant reduction in contact angle, and also friction coefficient also was reduced after the polymerization. Again, this is done only in the laboratory. So these are the materials that, these are at least the techniques that are used to modify lens surface in order to achieve lower friction and also better contact angles, and also lenses that avoid any kind of protein or lipid deposition. So in summary, what I have here is we have materials which are coming, which are promising in terms of bringing us more lower coefficient of friction materials, and also lenses that have anti-biofouling capabilities. And this is what we are looking for, and we do not know that yet how these are going to perform in reality. And these lenses are also not, these techniques are also not commercialized yet, and these obviously will be adopted by one of the major companies, and then they will also apply these techniques into their contact lens materials, and then we will have more clinical results coming. And that's why we do not know how these lenses perform or materials perform it on the eye. And that's the talk. Oh, that took exactly 1 hour.
Yep, exactly. I was just about to mention that. Thank you very much. First of all, I think it was a very, very wonderful talk. I think a lot of new things which a lot of us would have grasped from it. So we do have some questions already on the
Yes.
chat. So I'm just going to share my screen. And so the first question we have here, Dr. Vinod, is about the discomfort part, which we were discussing in the beginning of the talk. So with discomfort being caused by many different factors, what do you think, in your opinion, would be the percentage which comes from the material perspective of it?
Okay, I'll have to read this again. So
Yeah.
with discomfort being caused by so many different factors, what percentage of clinical discomfort is primarily caused by contact lens material? Okay, I'm rethinking. Oh no, I have no idea about this. I at least I have not looked into it. So I do not have answer for that one.
Okay, yeah, because I think in the beginning you made it very clear that there are many factors which can contribute to the discomfort, and your talk is basically on the material aspect of it, right? So I think the question comes from that perspective. Okay. So probably
as you might guess, because as I given my disclaimer at the beginning, I'm not an
yes.
expert in the field, but see, I've shared my knowledge, whatever I know. But whatever rest of the questions that have come up, if I have an answer, I'm going to happily give them the
Yes.
answer.
Yes. Okay. That's cool enough.
Yes,
The
that's
next
the
question
next
is
question.
about how do you measure the contact lens friction?
Friction on a contact lens surface. So I've read a few articles, and the way it was measured is by moving or rolling something on the lens surface, and that's what in a crux I got it. But in greater detail, I have no idea,
Okay.
because it's not a practical thing that we do every day.
Yes. Yes.
It's something which is done in laboratory. I've not even seen one.
Yep. The manufacturers would be probably doing this
Yeah,
more
that's
as
true.
clinicians. We don't really look at that in detail.
Exactly.
Yep.
Yeah,
That's true.
exactly.
Yeah. Yeah. The next question is about anything in mind we should keep as clinicians while suggesting re-wetting drops to our patients, consideration of the material perspective of the lens.
Okay, that's a very good question. So when it comes to riveting drops when putting on the eye, the things what we have to keep in mind is lens, the viscosity of the riveting drops that we are going to use, and the surface tension that it is going to create once it is applied onto the eye surface, because the surface tension of the riveting drops also is important. The surface tension of the lens and the surface tension of the lubricating eye drop or whatever you're going to use both are important, because the interaction between these two is what is interfacial tension is, and that interfacial tension dictates how the comfort is. So it's not just the surface tension of the riveting drops, but we should also know what is the surface tension on the eye. In most cases, we wouldn't know that one.
Yeah.
So viscosity and surface tension I'll be looking into. But one thing when it comes to viscosity is viscosity should not be too high, because if it is too high, it will become like a jelly, and then it will impede patient's vision or wearer's vision, and it's not very comfortable to put it on the eye or on the contact lens. At the same time, it should not be too low also, because that's the case, it's actually not promoting any comfort. So I think those are the things that we need to keep in mind when we are applying riveting drops. And also there are other things such as surfactants. Surfactants also are used in blister packs, for example, as I mentioned. So what kind of surfactants are used in riveting drops, also something consideration. So I do not know exactly which surfactants do better than other surfactants. So that's something I'll be looking into as well.
Okay. Next question is about what is the actual difference between silicone hydrogel and hydrogel lens surface in terms of physicality? And for example, the pores of the surface or the electron charge are different. So what's exactly the difference?
Okay, so silicone hydrogel lenses have more pores. You partly mentioned that, whereas hydrogel lenses are more, water bonding materials. So water bonding materials. So hydrogel lenses, because they are water binding, they tend to carry oxygen through them. So that's how the oxygen is transported. But in case of silicone hydrogel lenses, there are more pores, like open channels for oxygen to go through that one. So they use more open channels to get through the other side. So that's a physical difference between these two. But I'm talking about the lens bulk properties. But when it comes to the surface, it depends on what different material composition of the lens itself is. So some contact lenses, for example, hydrogel lenses, after addition of so many components, you either derive positively charged surface or negatively charged surface. So in case of silicone hydrogel lenses also, it's not necessarily the material, but there are other monomers or copolymers are also added to the surface. So it will still render some kind of charging. But I do not have exact details of this, but I think they will affect the surfaces as well.
Surfaces, yeah. And what about the plasma coating which you mentioned? Is it normally done on both the surfaces, front side as well as the back side? And would friction be between the lens and the lids?
Friction between the lens and the lids. So plasma coating is done, to my understanding, the plasma coating is done on the entire lens surface, both front and back surface. Okay. So what about the friction between lens and the lids? Are we not talking about only that one? Friction is measured on the lens. And again, how it is measured, I have not actually looked into. So yes, so whether I'm sure that this is done in laboratory, so they haven't actually applied lids onto it. So it's very laboratory measure at this stage.
Okay. And while measuring the friction coefficient, again, this is to do with eyelid, but again, I think you have answered that it's a laboratory thing. Yep.
Okay, so I have got one comment with that one. Eyelid tonicity play a role. If anybody can actually crack the eyelid tonicity bit, because lots and lots of people actually looking into, because eyelid tonicity plays a major role, be it the shape of the cornea, be it the pressure on contact lens while orthokeratology is placed.
Okay, yeah.
So it's a, if anybody does that, they might get a Nobel Prize.
Yes. So all the researchers out there, you got a clue from him if you want to study that.
No, because even in our building here, there are people who actually did do tonicity, eyelid tonicity, and they gave up. Even eminent researchers I'm talking about.
Okay, okay. Is there any way to measure the receding and advancing angles in vivo?
Is there a way to measure receding
the advancing angles?
I think I partly mentioned on that one that the in vivo is more looking at the tear butt.
Yeah, yeah. You can't really measure the angles because it's a material thing rather than a lens thing, right? Yeah.
Exactly.
Yeah. And how do we quantify the wettability in vivo for different contact lens surfaces other than the environmental factors?
I think we partly answered that from the previous question.
Yep.
For different materials other than environmental factors, I think first of all we can't measure in vivo. Yeah,
that's true. So we'll have to look at I think tear breakup time would give you the most exact idea, and comparing with different lens material, what you mentioned.
And also, if you were to compare how it performs using different environmental factors, for example, say if you want to assess in humidity per se, then of course you'll have to check tear butt in different humid situations. And then if you want to look at the temperature as a reason, then you have to look at the temperature. So you have to control for each factor and then look for DBUT. Yeah.
Yeah. And yes, we have discussed that there are many factors for discomfort, but clinically, is there any way to identify that the discomfort is actually caused by the contact lens surface? Is there any idea on that?
No, I don't think so. You can isolate one thing. So if I was a clinician, the way I see this one is you have a person with a discomfort and how I can help him with, right? So do I change contact lens material, or do I change or just give him a lubricant, or do I change XYZ? Is a very clinical decision, and I think practitioners are actually better at this than researchers these days, because they have an intuition actually to say that one lens works better than the other lens, and that is actually being very practical. And we don't have research evidence for that one. So if any good practitioners who have experience in this, if they would like to answer, I'm quite happy to have. We have Preeta here to probably she can answer a few questions.
Yeah. She has a few questions. I think later on we'll get to that and see if there's any inputs. Yep.
Definitely.
Yeah. Is there any impact on the electrolyte layer of because of the rubbing of the contact lens and all these coatings? Do you think that?
This is too early to comment about that at this stage. Now it's still at the experimental stages, so I don't have an answer for that one.
Okay. Yeah, because it's not commercially available anyway. So
no.
Yeah. Okay. What about any antimicrobial surfaces of contact lenses which are available for the allergic eyes? Any idea on that?
See, that's not my area. I know that antimicrobial contact lenses are available, but whether specifically available for allergic eyes, I have no idea.
Okay.
Yeah.
And yeah, because I think this is a question which came quite right at the end, because you were talking about the novel and the new contact lens technologies in terms of manufacturing the materials. So what could be the reason why are they not really being used by the companies? Is it because it's still very much in the research, or?
Some of these technologies, for example, click chemistry or labor technology were introduced like 15, 20 years ago. I think in terms of material sciences, how this is being done, I do not know. What are the other deficiencies of these technologies? We do not know. We know that these are being applied for lens surfaces now, but from a material industry point of view, I'm not sure what were the limitations. So I do not know. So again, something to bring into commercialization, apply to contact lens. It takes a lot of time. From an industry point of view, you need to experiment, you need to do research studies, and then apply it onto human eyes, and then clinical experimentally show that it actually works, and then only you can really market lenses. It's not an easy thing.
It's not very easy straight away.
It's not an easy thing. So just because something working, you can actually commercialize. It's not that easy.
Yeah, I understand that. And I think we'll take a couple of questions there. The questions are still coming in. I think we'll wrap it up with a couple of questions more. When it comes to these multipurpose contact lens solutions these days, these multipurpose solutions contain an additional lubricating agent. So what's your take on that in terms of the effect on antimicrobial? Again, antimicrobial is here, but in terms of this material, so if I were to,
I did conduct a literature search related to material wettability in focusing to not necessarily multipurpose solutions. Actually, when paper publishes, you can actually see that there's a section which is written dedicated or devoted to saying what MPS does in terms of comfort. But when it comes to antimicrobial activity or property and how the MPS affect on antimicrobial property, I'm not sure. I do not have an answer for that.
Okay. And when we say that the material has a neutral charge, or if it's a non-ionic or an ionic charge, how is the charge distribution, and what makes the positive contact lens surface to become neutral? It is about the material properties again.
So I think we did say that a contact lens material is made up of, so not just the major polymer that is there inside, or not the major component in case if you're talking about silicone hydrogel lenses, but we also have several other copolymers, monomers, homopolymers, and there are lots of other material components which are added. So if you ask, I think I did mention that if you have a hyaluronic acid, which is one of the things that you usually can use, it actually adds a kind of negative charge onto the surface. So depending on what component is added to base material is what dictates the surface charge.
Overall.
So I hope I answered that question.
Okay. And just we'll take one last question.
Yes.
It's about
Okay. Minimum protected area.
Yep.
So if I recall that paper correctly, so what we are actually that particular paper looked into an area where there is no break seen. So if you're actually using a kind of tear-scope kind of non-invasive tear breakup time assessment, you project area, and then you see that where the breaks are occurring. Okay, so we want we are looking at an area where it is actually protected more than the other one. So that means that you didn't see any breakage of tear film. So that was looked into. So if you have more breakage on the surface, obviously that means the amount of protected area on the lens surface is less. So if you have less breakage on the surface, so you have a more protected area by spread of the tear film. So that means that is protected well. So if you've got a minimum protected area in a large, which is large, that means it is protected well, which is what we want.
Yeah. Okay.
Now it was actually a pleasure again. As I say that I went through a lot of literature search for this one, and for me it's also a great learning experience. So I'm happy that I am able to share my knowledge with you guys.
Yes, and thank you, really thank you very much, Dr. Vinod, for doing this, and you know, at a very odd hour for you, and you know, the information what you have shared is actually phenomenal. I think you made that clear at the beginning that this is not your forte, but just by you know, taking up this topic, you had to undergo a series of studies to prepare for this topic as well. Yes. So thank you very much again, Dr. Vinod, from the whole entire team, OOLS and the attendees today. Thank you so much.
I also want to thank everybody, and thanks for everybody who attended the session. Thanks a lot.
Okay, well, we're all welcome. And I just want to make a small announcement that we are actually going to start a case presentation series in the nearby future. More details would be definitely shared via the email. So I'm just making a bit of announcement here that anybody who wants to share or present their cases, we would be very happy to have you present on our platform. It would be a 20 minutes case presentation session followed by 10 minutes of Q&A. So thank you very much. I'll see you all again next week. We do have sessions next week as well. Stay home, stay safe, and I'll see you all again next week. Take care and bye-bye.
Thank you. Bye.
Thank you. Bye, Dr. Bye.